Good morning, everyone. Myself, Jyoti Prasad, belongs to RMD Engineering College, EC department. Today, I am going to discuss about correlative coding. Prior to correlative coding, we had discussed about Nyquist criterion. Nyquist criterion for distortionless transmission. We had seen two cases, ideal solution, and we had some practical difficulties. We have seen the practical solution. So there, in order to get distortionless transmission, so in order to go for the better technique, we are going for the correlative coding, where we are adding some ISI say to the original signal, and at the receiver we will remove that ISI. And if we implement this type of technique, which is called correlative coding, we can achieve a bit rate of 2b0 bits per second in a channel of b0. So in a b0 bandwidth channel, we can achieve a bit rate of 2b0 bits per second. So this technique is called as partial response signaling scheme also. So this effect, whatever the effect we have added in the transmitter, that will be removed in the receiver. That is nothing but compensated at the receiver. So this correlating coding as a practical means of achieving maximum bandwidth, like I said, 2b naught in a bandwidth of maximum data rate of 2b naught in a bandwidth of b naught channel. So this is a correlative coding. So correlative coding introduce some controlled amount of ISI into data stream rather than trying to eliminate ISI completely. So even though we satisfy Nyquist criterion, some of the inter-symbol interference will be there. So for better transmission, we are adding some controlled amount of ISI, and we are removing at the receiver side. So there are three types of correlative coding are there: duobinary signaling, modified duobinary signaling, MARY signaling. So MARY signaling, MRI signaling scheme is extension. So first one we are going to see about duobinary signaling scheme. So the basic idea, the first one is the duobinary signaling scheme. So we are going to discuss about duobinary signaling. So for example, duo means double the capacity. Double the capacity. What we are doing here means, if I show you the transmitter diagram, you will get an idea. So consider a input sequence BK. Consider a input sequence BK. So consists of a binary digits 10 10 10 like that. So those bits are called uncorrelated. So the correlation between binary 1 and 0, which is adjacent, very poor. So that's why we are calling as uncorrelated bits. So each binary data, it will be like a rectangular waveform. Each bit duration, either binary 1 or binary 0, will have a bit duration of TB. So symbol 1 is represented by a pulse with plus 1 watt voltage. Symbol 0 will be represented by a pulse with minus 1 voltage. Minus 1 voltage. All of you know the rectangular waveform. So it will be represented a pulse. So when this sequence is applied to duobinary encoder, so like I shown, this is a duobinary encoder. So the dotted line section is called duobinary conversion filter, where we are giving input a binary sequence, and the delayed sequence also we are adding together and giving to a ideal channel filter. So this dotted line section is called duobinary conversion filter. So the input to duobinary coder we are giving is a binary sequence BK. After this duobinary encoder, we will get a sequence, output sequence CK. So that output sequence is a three level. How? Minus 2, 0, plus 2. For example, say this plus 1 volt is a plus 1 volt. Binary 1 is represented by 1 plus 1 volt. Binary 0 is represented by minus 1 volt. We will have how many combinations? 0 0 0 1 1 0 1 1. So four combinations will be there. So plus 1 into minus 1, plus 1 into plus 1, like that four combinations will come. If we do that combinations, we will get three values of output: plus 2, minus 2, or 0. So in this way, the binary symbol 1 and 0 will be converted into voltage levels in this block diagram. So the input binary sequence is BK, and this will be converted into voltage levels after passing through the Dio binary conversion filter, that we are naming as CK. So now, so what is the rule? At input, see here CK, how we are producing the original input sequence bk and the delayed sequence. If we add together both of them, we are getting ck sequence. So that one we can define the digit ck, output of duo binary coder, which is a sum of input bk plus bk minus 1, the delayed sequence. So here, if we apply this formula, if we get ck, if we see ck, the correlation between those things will be very high. Adjacent transmitted levels, we are adding some. So first sequence bk is there, bk minus 1, we are adding unwanted sequence. Okay, so this one is considered to be isi in a controlled manner. So this is called correlative coding. Let's see what is the impulse response h of f. I mean frequency response h of f, impulse response of impulse response h of t of the duobinary filter. For example, say for this delay element, this is the transfer function exponential of minus j 2 pi f tb. So if I take this transfer function for this line 1, so both if we add together in these two parts, 1 plus exponential of minus j 2 pi f tb. So thereby it is passing through the ideal channel filter. So if I multiply the ideal channel filter response hc of f, so we need to simplify using mathematical equations. So I need to convert this one into a sine or cosine trigonometric functions. So that's why one I can write it as exponential of j into exponential of minus j. So then it will become 1. So which is common in this one also. So that's why I will make the exponential of minus j pi f t b as common. I mean taking one component as outside, then here in the second component one will be remaining. If I take one outside, one other one will be remaining. And here minus j into plus j, if I take minus j common, the remaining term is e power j pi f t b. So this one we are going to write as cos pi ftb, the inside content. Exponential of j pi ftb plus exponential of minus j pi ftb. We will write it as cos pi ftb. So this response, we know hc of f, ideal channel filter, is equal to 1 if it is within the bandwidth of bit rate of rb by 2 bandwidth. So or else 0. So if I multiply this hc of f as a 1, then 2 cos exponential term. So this is the frequency response, the overall frequency response of duobinary signaling scheme, what we have shown in the figure. So if I plot the response, amplitude and phase responses, it will be like this. As we have two magnitude, the amplitude is 2, and it is spreaded over plus or minus rb by 2. And if we come to phase response, so same frequency is distributed between rb by 2 to minus rb by 2, and the phase it is having is plus pi by 2 to minus pi by 2. So easily we can get this response, frequency response. If I want to know the impulse response, I need to do a operation between two sync pulses. How? Why? Because means, how can we say this means I introduce a delay. So two sync pulses delayed by tb, two sync pulses displayed in time, displaced in time. That means the difference between those two things is minus tb. That's it. So the first component sync x sin x by x. This one sin x minus tb by x minus tb. So two sync functions. So the for the final output h of t, if I plot a response, it will looks like this. And the same thing between two sync pulses, we are adding and simplifying and making the term output a common term outside, and performing the LCM between these two things. After getting cancellation, we will get the term h of t. So detection, how we will do detection? So detection, if you want to see, you want to see the receiver. So what technique we implemented here, plus we have introduced a delay. The same compensation we should do in the receiver. What we added there, plus bk minus 1 at the transmitter. I did this operation at the transmitter. The receiver, what we will do, that the same value bk minus 1 I am subtracting from the ck. Here the cap symbol is there, which is denoted for the detected sequence, the estimate, the estimated output. The estimated output is bk cap. The input transmitted is bk. Input transmitted bit is bk. So, so we will check these two things. If both are equal, the transmission is 100% without errors. This is about correlative coding. Thank you.